And we're rolling.
Correct? Okay. All right, guys, last section, we're talking about the Doppler effect and how that can impact your frequency, your observed frequency of a longitudinal sound wave. I've been told by my cameraman to move this direction. All right, here we go. So, real quick, before we get into the Doppler effect and all that, I want to talk about the fact that the temperature of air can actually impact the sound waves that travel through it. Okay, so we've got an equation, which I've got written at the very top of the board, which just tells us that when we're talking about the velocity of a sound wave traveling through air, it is actually impacted by the temperature of the medium, okay, which for us is air. That's the substance it's traveling through. So we've got this lovely equation. The velocity of our longitudinal wave, sound wave traveling through air is going to be 331.5 plus this 0.606 times the temperature, okay, of the surroundings. So, and that temperature needs to be in Celsius. Okay, so that's just an equation for you to use to understand that the outside air temperature will actually affect how quickly a wave is going to travel through it. Okay, so now we're going to move on to the Doppler effect. Okay, so the Doppler effect has to do with the nature of sound waves and the observer of those waves. When a sound wave is in motion, a stationary observer is basically going to hear each wave crest, right, as if it's moving toward it. Then each wave crest is going to be emitted from a closer position, okay? Now, obviously, you're talking about something that's continuously making sound, right? It's not, you would not notice the Doppler effect quite as much if the sound is coming at you intermittently. Does that make sense? So when you've got a continuous sound moving towards you, then each time the wave crest hits you, it's actually being emitted from a position that's closer to you, okay? So the frequency is going to be larger due to the shorter period of time for the wave to reach you. So if the frequency is larger, then obviously your pitch is going to be higher, okay? However, and that's what we've got going here, right? So we've got this continuous wave coming at him. So each time the crest of the wave hits them, it's hitting them from a closer position. However, once this object then moves past the observer, right, they still can hear the sound. It does travel to them, but now the crests are further and further apart, okay? So those wavelengths, the wavelength doesn't actually change, but sorry, there's distraction noise behind me. But it's coming at them from a further and further away distance. So what happens is that basically causes your observation to be that the sound has changed or lowered in frequency. Okay? Has it actually changed? No. But the frequency at which you're hearing it actually does change. And we have this handy dandy little formula to help us calculate what the actually observed frequency would be. So here's our equation. It's the frequency observed equals the velocity of the sound plus or minus the velocity of the observer over the velocity of the sound plus or minus the velocity of the source. Okay? Now that might seem kind of tricky and not clear, and you have to actually, hang on, I'm looking for my thing here. Okay, it is. You have to actually engage your brain to make sense of this equation. So here's what we know. We know that when a sound is traveling towards us, we believe or we hear it at a higher frequency. Okay? And when a sound is traveling away from us, we actually hear it. It hasn't changed frequency, but we hear it at a lower frequency. Okay, so how do we then determine how to use this equation? Well, it's really fairly simple. Okay? So first of all, we're going to look at if the source is moving. Now the source is my Vs up here in the top and the bottom. Okay? If the source of the sound is moving toward the observer, I know by what I know about waves that I'm going to hear it at a higher frequency. So I basically want to come up with a larger frequency, so I want this value to be greater. So if my source is moving towards the observer, I'm going to take the velocity of the sound, and I'm going to subtract, this is the source is moving, sorry, down here. Oop. sorry. Okay, so if the source is moving, I'm going to take the velocity of the sound and subtract the velocity of the source. That's going to make this whole number be smaller, make my denominator be smaller, which makes my frequency then be larger. That's what I'm looking for, right? Because if the source is moving toward me, I know I'm going to hear it at a higher frequency. So I want my observed frequency to be higher than my true frequency. Am I cut off? Okay. So that's if my source is moving toward me. What about if my source is moving away from me? Again, if the source is moving away from me, as we have up here, I know I'm going to hear it in a lower frequency. So I have to manipulate my equation so that I get a frequency, an observed frequency, that is lower than the true frequency. So what I would do is I would take the velocity of the sound and I would add to that the velocity of the source. Okay? That's going to make my denominator a larger number, which will make my frequency, oops, sorry, plus, make sure I got this right, lower, smaller, yeah, sorry, yes, sorry about that. So I'm going to add this, which is going to make my denominator larger, which is going to make this number, my observed frequency, be smaller. Okay, so that's if I've got the source that is in motion. Now, what about if it's not the source that's in motion? What about if it's the observer that's in motion? Again, if I am moving toward the source as an observer, I know that I'm going to hear the observed frequency as higher than or greater than the true frequency. So I'm looking at the denominator of my equation for this half of it. So if I am moving toward it, again, I want a higher frequency, so I'm going to add velocity of the sound to the velocity of the observer. That will give me a larger frequency because it will give me a larger denominator of this fraction. If I am moving away from, if I'm the observer and I'm moving away from the source, then basically I'm looking to get a lower observed frequency, so I've got to make this denominator, right? I'm going to make that be smaller so that my denominator is larger and my observed frequency is smaller. Okay, so I'm going to take the sound, and I'm just going to the velocity of the sound. I'm going to subtract from that the velocity of the observer, and that's going to give me a smaller frequency, which should make sense logically. Now, one other situation: what if the source and the observer? How does this equation work if both the source and the observer are stationary? So what happens in that case? Well, that would mean that the velocity of the sound, if the observer is not moving, then that would mean that this would go to 0, right? And if the source is not moving, that would mean that this would go to 0. So what I end up with is that my frequency observed equals the velocity of the sound divided by the velocity of the sound times the frequency, the true frequency. Obviously, the velocity of the sound over the velocity of the sound is going to equal 1, which means that my frequency observed is going to equal my true frequency. So this works mathematically if nothing is moving as well. And that was just to show you how that actually works. So, okay, I think I have one more section, then we'll be done. Can you stop that, please?
Wait.
Guys,